we call it a Talk2D series, essentially where we invite leaders in the field of 2D materials to deliver talks to our industry partners and the staff and students of the hub. Other people are also welcome. I've seen a few people who are not affiliated to the hub, but that's fantastic. All right, so let me give a brief introduction. We are very fortunate to have with us on this online presentation Dr. Vincenzo Palermo. He's the director of the CNR Institute for Organic Synthesis and Photoreactivity. For people who do not know what CNR is, it is a National Research Council of Italy, the premier research organization of Italy. More than that, I think he has been the vice director of the EU Graphene flagship program, which we all know has been a massive investment in Europe, over $1 billion in the last 10 years. And he visited Monash as part of the EU-Australia workshop on graphene and 2D materials, and he shared some of the experiences which he had over the years working for the EU flagship. Another important point I noticed was that Vincenzo is an excellent storyteller. Like all Italians, he's a fantastic storyteller. He's an excellent science communicator. And with that, I will stop and let us hear from Vincenzo.
Thanks very much, and thanks for inviting me. I'm sorry I could not be there in person, but maybe another time we'll manage to meet again. It was really nice to meet you and all your colleagues from Monash last year, and I really enjoyed my staying there, and it was really interesting to see what the Australian community is doing in our field. So today I will give an overview of what we do in my group about using 2D materials, mostly graphene and graphene oxide, and we use them for different applications, but in particular, I will focus on applications for energy storage. First, a small introduction where I'm talking from. So I'm currently located in Italy, in a city called Bologna. It is known for being the oldest university in Europe. It was founded in the 9th century, so in the early Middle Age. It is more or less in the middle of a triangle in the north of Italy, between Milan, Venice, and Florence. If you don't know Bologna by name, maybe you know some of the companies who are located here. It is very famous for being a hub for technology, in particular for mechanics. All the big luxury companies, car companies of Italy are located here around, like Ferrari, Lamborghini, Maserati, also motorbikes, Ducati, Aprilia. They are all, let's say, 50 kilometers around Bologna. It's also famous for food. Maybe you heard about Parmesan or tortellini or Bolognese sauce. That's also very famous export. But everything related to materials and mechanics. So there's also a strong leadership in packaging machines and in ceramics, even if in that field maybe China and Turkey took over Italy in the last years. I am part of the National Research Council of Italy. This is not a university, it's a government institution, so it's the largest research institution in Italy for a number of researchers. We are around more than 8,000 people among researchers, scattered all over Italy in more than 100 institutes, with lots of secondary sites. CNR even has 2 bases in the South Pole with a large budget. And Bologna hosts one of the largest research areas of CNR, with around 1,000 people working here every day. I am the director of the Institute for Organic Synthesis and Photoreactivity. So this is the research area. My institute is these 2 buildings, is the largest in Bologna. And it's mainly focused on synthetic chemistry, photochemistry, and material science. So we have in our institute all the value chain that goes from the synthesis of the small molecule to its assembly in larger structures, in coatings with those solar cells, LEDs, but also composites. There is a lot of activity on biomedical. So it's a pretty wide range of activities. In particular, in my group, we work a lot with the graphene and other kinds of two-dimensional materials. Since the beginning, I've not been too much interested in the first classic application of graphene, let's say the Nobel Prize winning field where you talk about transistors or twistronics or Dirac fermions, so all the hard physics parts. But we always thought it as a tool, as a new building block in our portfolio to create new structures, so not just in layer, but really bulk materials that then you can use in composites or in lots of other applications, combining graphene with other kinds of polymers, nanoparticles, biological molecules, and so on. And so we use this kind of approach for lots of different applications. So to as example, functionalize graphene to enhance its interaction with living cells, to use it in nanocomposites, also for aerospace, automotive, for energy storage, for gas filters and water filters. Last time that I was in Monash, my presentation was mostly focused on water filters, but this time I will talk more about energy storage. It's also a very interesting field that we are working a lot on. In particular, what really passionates me is to understand how these kinds of 2D materials can allow us to get new behavior of molecules and solvents when they are constrained in this kind of environment. When we have nanosheets that you can stack over each other, and you can engineer the space, the chemistry, the atoms that are in between, of course, you create a new environment that it's not a three-dimensional environment, it's not a surface, it's something different. It's like a two-dimensional solution where molecules and water and lots of other ions will behave differently from how they behave in a bulk solution or normally. And so I always find this very exciting and very stimulating. But let's go to the main topic of today, is about challenges to improve cathode materials in batteries and supercapacitors. Of course, batteries and supercapacitors are key to save the world in the future. We really need to develop sustainable energy, and storing this energy is even more challenging than producing it. Now we can produce a lot of solar energy, wind energy, but we are still lagging behind oil or fossil fuels in our capability to store these kinds of energies. And there are lots of fields that we can improve. Current batteries are good, but they can become even better to beat oil and gas. Things that we can improve are, as example, enhance the ionic conductivity of our materials, because the penetration, the diffusion, the intercalation of ions in our anode or cathode is often the bottleneck of that avoids fast charging. Then, of course, we also can improve electronic conductivity, because lots of materials that are very good to store, as example, ions, are very bad conductors. Of course, we want to have a high specific surface area. That's why we want to go nano, because we want our materials to interact very well with the electrolyte, again, for speed. And another problem of lots of these materials, think to silicon as example, is that they can store ions very well, but at every cycle, they change their volume a lot. So if you have large bulk amounts of these, they will crack and get destroyed. So that's another reason why we can go to nanocomposites and to add other materials to really improve this mechanical stability. Of course, we don't want the material to self-discharge. We want to keep this charge for long. And another thing that we want to do is having more options. So it's not that one thing will fit all. So lithium ions is, of course, the most successful technology at the moment, but we can have even other crazy ideas to change the ions, the electrodes, the materials that we use, because of course this will give us more options. How can 2D materials help in this? Well, on a very fundamental level, having something that is two-dimensional, truly two-dimensional, that we can process, we can functionalize, allow us to build new kinds of architectures at the nanoscales. We can use these kinds of nanosheets to wrap nanoparticles, as example, to just mix them or to make layer materials, sandwich, multi-layers. And we'll see some examples of this. So in summary, that's what we do, and that's what we like to do. We use these kinds of new animal in the zoo of nanomaterials to create novel architectures to solve some of the challenges of energy storage. One of the materials that we use most is graphene oxide. Graphene oxide is, at the beginning, was really underestimated by the graphene community because, of course, it's highly defective, it's not conductive, you cannot do very good transistors with it. But to joke, sometimes I tell to my friends of the community that there is only one truly two-dimensional material that we currently have, which is graphene oxide. If you work with the other materials, usually you never have monolayers, and what you have is a mixture of, if you are lucky, monolayers and multi-layers in a very bad solvents like N-methylpyrrolidone or other kinds of solvents. And usually the aspect ratio is tiny. You have 500 microns, 2 micron, 500 nanometers, 2 microns flakes, few monolayers, some multi-layers. With graphene oxide, you don't have these problems. You can have huge nanosheets. They are all monolayers. They can be 1 nanometer thin and 100 microns wide. So it's really a nice material to work with. And last but not least, you can really process it in lots of different solvents. These are all kind of solution of graphene oxide that we could obtain in different kinds of solvents. Because there always been this kind of comparison. On one side, we have graphene that is, of course, the wonder material, beautiful, perfectly hexagonal honeycomb lattice, incredible mechanical properties, electric properties. On the other side, we have graphene oxide that is highly defective, a bit of sp2 carbons that can conduct charges, but mostly sp3 holes, any kind of chemical oxygen functionalization. So it's not very good to conduct electricity, and also the mechanical properties are worse. The good thing is that it's not one way or the other. We can even start from graphene and oxidize it just a bit, or take graphene oxide and reduce. So we can really move back and forward from one extreme to the other, as example, using reduced graphene oxide. So which one is best? Of course, it depends on what you want. So if you want performance, you need to go on the side of graphene oxide, or graphene, because you want to increase electric properties. On the other side, if you want processability, you should go on graphene oxide, because all these defects make it highly processable, and then you can also play chemistry on it, you can functionalize it. And of course, to obtain graphene, you can use exfoliation in solvents, you need a lot of energy, you get low aspect ratio. On graphene oxide, you can use chemical oxidation, which can happen even at low temperature, but it requires harsh chemicals. What we use a lot is also electrochemical exfoliation to obtain electrochemically exfoliated graphene oxide. And we use a lot electrochemistry. We use the power of electrical forces to really deposit materials, but also to exfoliate them. This allows you to start from graphite and produce EGO that is maybe less oxidized than graphene oxide, and you can even choose how much, where you want to stop along this arrow. So how much you want processability versus performance. And RGO, of course, is not as good as graphene. It does not have incredible properties, but the charge mobility can anyhow get pretty good in the best condition. And several groups have claimed mobilities, high charge mobilities, even up to 5,000 square centimeters per volt per second. So maybe it's not good enough to make novel transistors or novel microchips, but it is good enough for batteries of supercapacitor, better than lots of polymers. So talking about challenges in energy storage, a problem, as I said, is that we have a lot of energy, but this energy usually is not available when we need it. So the energy demand is not synchronized with the energy production. So to overcome this, we need batteries, we need ways to store these kinds of batteries, and lithium is not good for this because we need a lot of batteries that should be cheap. And another problem with lithium is that it's not very well distributed everywhere. So not all the countries have lots of lithium, and there are also debates on how much lithium will be needed to, as example, replace all our cars with electric cars and have all the batteries that we want. Of course, if we look at chemistry and at the periodic table, there are some alternatives to lithium. Here you see this very nice periodic table made by some of our colleagues that where every element has an area in the table that corresponds to its abundance. And the green ones are highly abundant, the yellow one not so much, and the red ones are really in serious have a serious problem. And you can see there is even an icon that shows you all the materials that we need, as example, in mobile phones. Lithium, of course, is very important, but it's not so abundant, but it's very important. Of course, we could think to something that is as light as lithium, a bit heavier, but it has the same chemistry, and this would be sodium. A difference from lithium, sodium is really abundant. We have it in the seawater. So having sodium batteries, sodium-ion batteries would be really ideal for us, for energy storage. The problem is that in batteries, the key thing is to be able to intercalate our small ions in our materials. Our anode on one side, that is typically graphite, and cathode on the other. That is you can use different kinds of materials. But anyhow, the key step is that these ions should go in between these layers of graphite, as example, and stay there and just go out where we want it. Bad thing is that if we look at graphite intercalation compounds, sodium is the most difficult material to intercalate. So it's not so easy as lithium or even other larger ions. So it's not just a matter of space in between the layers. It's an unlucky combination of ionization and coupling energies. You can refer as example to this paper that it's not from us, but it's a nice paper showing this this problem. So this makes the intercalation energy of sodium the highest among all the materials of its groups. And so sodium has the weakest binding among all 5 alkali metals, and this it's not just for graphene. It's you can see on the graph here on the left that it's a problem with lots of two-dimensional materials. So we would like to intercalate sodium easily in this kind of material, but it seems really hard. How can we do it? Well, now that we know how to exfoliate graphene, we can exfoliate it, work with the chemistry, engineer it, and reassemble in a way that maybe it has larger space and better chemistry for sodium. So in the first example, I will talk about how to enhance ionic conductivity, but in case In this case, is really how to intercalate sodium and to understand how to intercalate sodium. So our idea was to exfoliate graphene and then functionalize it, in this case with a molecule that has two functions. One is to act as a spacer, and the other is to stabilize sodium ions in a certain position. So to cut the story short, we use very clean graphene because we really wanted to understand, to have a very clean environment. So it was not for, let's say, bulk application, but in this case, really few layers just to understand the concept. And we functionalize it using the diazonium salts and nitrobenzene, which I'll explain later why we choose these kinds of molecules that then we reduce to aminobenzene. And so you take one layer of graphene, and then you attach molecules on this, and then you can add another layer of graphene, and then functionalize it and over and over. In this way, you obtain these kinds of very structured but very clean, with very few system with very few defects, because we start from high quality CVD graphene, and the chemistry that we use, this diazonium salt chemistry, is really clean. It creates a radical and nitrogen as byproduct, so there are no possible other kinds of contamination. We obtain these kinds of graphene sheets that have aminobenzene molecules only on one side. These kinds of graphene with functionalization only on one side is called Janus graphene. This comes from an ancient Roman god that had two phases, so that's what gives him the name. So what do we do practically is to take one layer of graphene, functionalize it, then we float it, we detach it from the original copper surface, and we deposit it on, in this case, silicon. And then we can repeat this thing again, so to have several layers of this. And this allows us to have a few layers of graphene, but with large scale. So we can, this is not something nano, you can really see it by naked eye, and here you can see some of these samples. And you should think that all this sample is a uniform layer of graphene, multi-layer of graphene, and each of these layers has been functionalized with the molecules. Here is some characterization. You can look at it as example by optical microscopy, Raman mapping. This is the cross-sectional TM, and of course Raman. And you can see here that the initial graphene, that is this black line, has basically no peak, no defects. Then when you functionalize, you see this band increasing. So all the characterization confirms that what we have is really something with very few defects, with exactly only the molecules we want in this material. Then we use also some computational methods like density functional theory to check first that the most favorable configuration of these kinds of aminobenzene is standing vertical, so it really acts as a spacer, and what you get is this kinds of situation. And of course, if we intercalate sodium on lithium, we can see that, of course, sodium is a bit bigger, it's more comfortable with the slighter interlayer distance. Besides just looking at the interlayer distance, we also use DFT to calculate the most favorable position of sodium in this case. And we choose these molecules because the aminobenzene interacting with graphene creates this kinds of a favorable spot for sodium, where sodium has the lower energy that you can get in this kind of intercalation. Sodium ions then can be stored and can stay in different position, as you see on the right part of the slide, but and they are all good, but of course the most favorable is this one. So this molecule acts as a spacer, but it also favors the storage of sodium. Does it work? Well, you can, because the system is so thin and so flat, it's very easy to monitor intercalation by Raman. If these ions intercalate, the G band that is more or less here should move. And here we can see that when we try to intercalate sodium in graphite, there is no change of the G band. Also in stacked graphene, not functionalizes like this. If we look at intercalation of in our genus graphene, you will see a change and a disappearing of the G band. Also the D peak and the 2D peak disappears during the charge and the discharge. So this is already a clear evidence taking in real time that the sodium is going into the material. And you can also plot at different voltages the position of the G-band peak. So first we did the try with lithium, and you can see that when you get close to 0 volt, graphite, graphene, and even our aminobenzene graphene show a clear change of the G-band shift. Some points here are missing because the G signal gets too low and the signal-to-noise ratio gets too high. With sodium, the situation is different. In graphene, no change of G peak. In graphite, no change of G peak. The only way to intercalate sodium is through this, thanks to this aminobenzene graphene. One particular thing is that this kind of intercalation is different from what you get in graphite. So in graphite, you get this stage intercalation where ions enter first in one layer every 4, then one layer every 3, one layer every 2. This does not happen here. So all the ions enter at the same time in all the layers. And what we did was to combine, because we have these samples pretty large and pretty thin, we could combine Raman observation, so see the intercalation in real time by Raman, but combine it with lots of different other measurements, like measuring, as example, the current that goes in and out, and measuring the shifting of lots of different things, like the IDG ratio, the 2D band intensity, the G band position. But we wanted to do even something more. We wanted to see it also in real time. So we use this particular technique called imaging ellipsometry. And this is like normal ellipsometry, but it has lateral resolution. So what you can do is to ramp the potential in your material and do a map, and you can see in real time that the environment between the stacked graphene changes, so you can see the ions entering in real time. And you can take a movie of that. So what you see here is a movie of this material that goes from red to blue. The blue is when the sodium ions are going in. I don't know if you, are you seeing the movie? I'm not sure it works. Philip?
Yeah, we can see the movie.
Okay. So you can see that it goes all blue when the voltage approaches 0, and then when you go back to the initial voltage of 3 volt, then the ions go out, and it really you can get this in real time. So it's pretty nice and interesting technique. Moving to another example, in this case, we want to improve the electron conductivity, but also the mechanical stability of our materials. And we go a bit more toward bulker structures. So what we do is to use graphene or graphene oxide to create tridimensional structures. And then we put on this kind of graphene that acts as an electric conductor, an active material for lithium storage, in this case, that typically has poor conductivity, poor mechanical stability. But thanks to the graphene, we can improve its properties. And a good thing of graphene is that you can, it's because it's so flexible, it's so conformal, you can deposit it on lots of different, even on complex shapes, and it will follow the shapes. And once you etch or remove the shape, it will remain there. So you can use a sacrificial template, which could be a metallic foam or even a polymer, whatever, to create your structure of graphene. And then you remove the template, and what you get is a foam or a structure that is all made of thin layers of carbon. That was the concept. This is an example of how it looks. So you can take, as example, a nickel foam, nickel sponge that is pretty cheap. You coat it with graphene. In this case, we coated it with electrochemically exfoliated graphene oxide, but you can even grow graphene directly on the sponge. And then you can even add your active material for lithium storage. So here you see three samples. The first is just nickel, the second is just carbon, and the third is a sponge of carbon graphite foam coated, in this case, by iron oxide. And this is how it looks. And if you zoom in, you will see a porous layer of this active material that can then be tested in coin cells for energy storage. And the tunability and the processability of the process is very nice. The problem of iron oxide often is that it's not a good conductor and it tends to detach. So with the cycles, it will crack and go away. So what you can do is to take a substrate of CVD graphene, which is highly conductive, and then you deposit your material on top of it. And then you can even, what we did was even to put a layer of porous electrochemically exfoliated graphene oxide on top of it. This would increase the stability of our material. Imagine it like a sandwich. But using electrode deposition, you can repeat several times this process, so you can have multi-layers that will increase your ion storage capability. And this is how it looks like. And of course, you have a multi-layers, and so imagine that you can have a Mac, a burger, or a Big Mac. And of course, the Big Mac is much better. Bit of detail of how it works. You start from a graphene foam, which can be CVD graphene, so pure graphene, and then you do a electrode deposition from sodium acetate and iron ammonium sulfates in water and ethanol. So you obtain these lamellas of iron oxide hydroxide, and then by thermal annealing, you transform it in your active material. Of course, this is if you want just one layer, but you can coat and then you can have these kinds of multi-layer structure. And then when you do the thermal annealing, you transform the hydroxide in iron oxide. And at the same time, you transform the graphene oxide in reduced graphene oxide that is more conductive. This is a cartoon, but these are real images of the material that we obtain. And you can see in particular in this one that you can clearly discriminate the different layers of these kinds of materials. This is some kind of electric performance comparison, and the blue line here is the one that has 3 of these layers, and it works much better than the simple coating and the 1 or 2 layers, both in specific capacity and cycle number, but also if we measure the specific capacity at high charging and discharging rates. So after 1,000 cycles, we had the capacitor retention of 84%. I go quickly through other examples. In these other examples, we wanted to improve the mechanical stability, but also try something a bit different. So try something that it's not the classical battery or capacitor, but an original geometry. In particular, in this example, I show an example that is not related to batteries, but to capacitors. In particular, micro supercapacitors. These are a bit like, let's say, interdigitated electrodes or transistors, but the goal is not to transmit a signal or amplify it, is to store charges electrostatically very fast. And of course, you want to have a lot of charges stored. So you have these electrodes, anode and cathode, that are interdigitated. They should be at microscopic distance with each other. These kinds of devices have thin layer structure. They can have high power density and rapid charging and discharging because there is no chemical reaction involved. They have long life cycles, so they are really, really interesting, maybe not to store large amount of energies, but for electronics. And of course, you can have just a metal to store these things, but it's ideal to have different kinds of materials. As example, metal oxides are very good for these kinds of storage because they have different kinds of potential windows. And ideally, if you have two different materials on the anode and on the cathode, you could even combine, I mean, you have a wider potential window. So this means that you have a higher capacity. But the problem is how to deposit these kinds of materials in these kinds of small of small electrodes. You can do it with lithography, of course, but that's really expensive. It's not really for cheap materials. What we did again was to use given that we have to coat electrodes, why do not charge these electrodes to favor the coating? So we start with the electrodes that are made of exfoliated electrochemical graphene that is conductive. Then we apply a positive voltage on one of the electrodes while it is immersed in a precursor of manganese oxide, and we have a deposition only on that electrode. Then we apply voltage on the other electrode in a different solution with a precursor of iron-containing molecule. In this way, what you obtain is an asymmetric micro supercapacitor. The reaction that takes place during the deposition, not during the functioning of the capacitor, is this one. So basically, you have ions in solution, then gets deposited and gets oxidized. Then these ions transform in an hydroxide and then in an oxides further on. This is how it works. So we use manganese acetate as a precursor of manganese oxide. So you deposit manganese acetate, you apply your bias to one of the electrodes, then you remove the solution, then you apply ammonium iron sulfate, so you change the solution, and you apply voltage to the other electrode. And then this is the kind of morphology that you get. It's nice morphology, ideal for what we want, because we have these kinds of, here it's not so clear, but they are kinds of, let's say, vertical disordered flakes with the nanometric structure, but significant thickness, so 100, 200, 300 nanometers. So this gives you a lot of material and a lot of active surface to check, to store your ions. Another thing that we did here and we demonstrated here is that we use pulsed current. This is another advantage of electrode deposition, that it's really easy to tune, of course, the voltage that you apply, the time, of course, but also you can use different kinds of voltage shapes. You can use square waves, sawtooth waves, or whatever. And here you can see a comparison that if we do the deposition just applying a voltage, it works, but the adhesion is not so good and the film detaches, while instead if we use a pulse deposition, it gets better. The quality is better. This is not new. This is well known in electroplating, even for metals, that using these kinds of pulse, you give more time to the ions to replenish, and it's basically most efficient. So this is a comparison of the specific capacity. First, if we use just bare electrodes, the performance is the black line here. So it's pretty low. In this case here, we have symmetric capacitors. So if we deposit iron on both sides, we get a capacity that gets up to 800 microfarad per square centimeter. And of course, the more we deposit, the better it is. With manganese, also a bit less. But if we have the asymmetric capacitor, like in this case, we get to 1600, so more than double the capacity. So these are really good performance if you refer to the in the paper that we publish on this. We even did a comparison with other kinds of data present in literature. So it's pretty a good performance. And of course, being these micro supercapacitors, the stability is pretty good. So after 10,000 cycles, the stability is still comparable to what was initially, and also the Coulomb efficiency stays to 100%. Last example, I just conclude with a more strange and original example, or a more original geometry that tries really to think out of the box to solve the problems of batteries. A problem of batteries, in particular for cars or airplanes, is that they can be powerful, but they are really heavy. So this limits the autonomy of a car. Ideally, you want to have lighter batteries, and lots of people are trying to make lighter and lighter batteries. A completely different approach is to use the car as a battery. Now, most of the cars of luxury car or electric cars are already made of carbon fibers. And if you think a carbon fiber is not so different from a graphite anode, it's made of carbon, of course, it has a lot of sp2 carbon atoms, it can be electrically conductive, and they are all connected like an array of electrodes. So in theory, you can have different layers of carbon fibers and use them as the anode and the cathode of a battery. You can have some porous polymer in between to ensure continuity, but in the pores, you can have an electrolyte. This way, you could have distributed batteries all over the car. Of course, these batteries will not be very good. The performance will not be as good as a normal battery, but they can provide energy storage in addition to a battery, so allowing to reduce the weight that you are bringing around in the car. This is a very nice idea. It's not from me, it's from one of my colleagues called Leif Asp in Chalmers, and in 2018 has been selected as one of the top 10 scientific breakthrough in the year. So we thought together with Professor Asp, we thought to use our approach to get to this goal, because of course pure carbon can be good as an anode, but it cannot be used as a cathode. So you need to find a way to functionalize, to coat these carbon fibers. And this is not easy because it's not just one carbon fiber. It's an array of carbon fibers. You need a cheap, effective way to coat them. You cannot just dip in a solution because they are already often arranged in an array or in a yarn. So what we did was, again, to use electrostatic assembly and electrophoretic deposition. We take the material we want to use, so lithium iron phosphate, and we treat it with a positively charged polymer. Then this allows electrochemically exfoliated graphene oxide again to coat it. This will protect it, will make it more conductive, but in this case, it also makes it allows it to be absorbed on carbon fiber. So we charge the carbon fibers and they attract these kinds of particles, create a huge amount of material deposited on the carbon fiber. So here you can see some images, and in few minutes you can go from bare carbon fibers to a coating. So of course, the ideal coating is a thin coating. Here it's just to show that if we got to very, very high voltage, you get a huge amount of material deposit. That this would be too much, but we just wanted to see how far could we go with this method. So this is a very fast and tunable and cheap way to coat complex geometries like yarns of carbon fibers. And this was then tested this was in a half cell, this kinds of carbon fiber coated, and then in full cells that was tested as well in Chalmers. And this approach is compatible in industrial application, and I really hope that it will be used one day in real applications. So this was my last example. I think I've run out of my time. Give me 1 minute to thank all the people that contributed to this work. in particular my group in Bologna. I work for part of my career in Sweden. Now I'm fully I'm fully located in Bologna, but I am affiliated professor in Chalmers. Still keep a position there as affiliated professor, and I still have lots of collaboration. And most of the work on energy storage, I should say, is done in Chalmers. If some of you or some students that will be interested in coming to Italy or even to Sweden and they like to work in these kinds of fields, please let me know. We are really looking for smart students to come and get a PhD or even postdocs. I did a very quick tour among many different applications. You can refer to the papers I cited in some of the slides, but if you just want to have the whole package in one point, you can refer to this review that we published in a special issue last year, where it really first describes all the papers I mentioned to you, but also try to give a structured discussion on all the challenges that we need to face to improve batteries and supercapacitors, and how graphene can help us to solve this. With this, I conclude. Of course, you can contact me if you have other questions and or curiosities. If you pass by in Bologna, please come and visit us. And I just finish with this. I really, again, as I said at the beginning, I really appreciate Melbourne and Australia. In particular, I love a lot the nature you have there, incredible nature, but also the city was nice. And I thank you for your attention.
Thank you, Vincenzo. That was an excellent talk. I think connecting the dots of various aspects of engineering electrodes with graphene, I think that's a fantastic talk in many ways. I think the session is open for questions. Please, you can unmute yourself and ask questions to Vincenzo. And if you can raise your hand, that's probably easiest way to conduct this.
Yeah, I see that Manas Ranjan Panda is unmuted.
Manas, you want to ask a question?
Yes.
Hello. Hello.
Hi, Vincenzo. Yeah, this is a really very informative talk. Yeah. So I'm very impressed about the in situ Raman you have shown here. So I have like few queries regarding what kind of electrolytes you have used and what type of setup you have used to record the in situ Raman data. If you can give insights, that will be really great.
You mean, well, let's. If I can just go out. Yeah, maybe it's quicker like this. You mean in this case?
Yeah.
I should say now the Raman was a standard one. I should say I don't remember by heart which kind of Raman we did use, but it's a commercial Raman, and here the key thing is to have. Let me go back to these kinds of samples. This is the key thing, and if you have a powder, if you have a paste, then of course the situation is not as clean, and it's really more difficult to use all these techniques on top of it. While if the key thing to really be able to observe this thing in real time was to have these kinds of order layer. Of course, they are not perfectly overlapping, but you can really see all the single layers. You don't have ripples. They are all the molecules, all the things are oriented in the same way. In this way, it's really easy to map everything. And for the solvent, let me.
Yeah, electrolyte.
Yeah, no, sorry there.
Maybe Manos, you can check the article that has been published.
Okay, yeah.
Yeah, now I can send you the article and see it,
Yeah.
but now I don't remember. But it was the standard. I think it was a carbonate, similar to what typically is used.
Vincenzo, I have
Thank
a
you.
quick question about this work. This is a really exciting work because I have not seen many papers report the ability to intercalate graphene structures with sodium ions. This is fundamentally really interesting. But have you thought about strategies in bulk graphene materials? Because obviously, if you think about it, fundamentally this is exciting, but real life, you know it. I mean, it will be challenging. Oh,
Yeah.
Is it possible to think about the strategies which you have already described in bulk graphene materials?
Yes. There is some work ongoing, because of course, if you do this on I mean, the goal here was to do it on CVD graphene, because we didn't want any other kinds of effect.
Yeah.
We just wanted graphene and this molecule to really show that it's working. You can attach the same molecules, as example, to graphene oxide in powder, and do then have a bulk material, a powder that then works. Work is ongoing on this. We have demonstrated some of this material as example. That's another application for lithium-sulfur batteries, but for sodium, we are still working on it, and we don't have publishable results at the moment.
All right. Thank you. Thank you very much. Any other questions from the audience?
Means my
Maybe
I
will ask a bunch of questions once again. So with the I'm really interested in the sodium-ion battery work, and I just want to quickly ask, have you done any devices with this material, and what sort of performances do we get actually in terms of okay.
That's actually when we finally managed to publish it was a thing that we had to really state clearly, not to mislead people, that of course, if you talk about, I don't know if you still see the slides.
I can see the slides, yeah.
Yeah, but if you think that you have, let's say, 1 square centimeter of material, and this is really, in this case, 7 layers of graphene. So the mass of this electrode is really tiny. So you cannot do a device with it. What you can do is to measure current going in and out. This can get to the microamperes, but of course, this is not a battery. This is an electrode that is needed to demonstrate the battery.
Correct. Yeah. So that means that there are levels of innovation required to make it, a more practical and more durable. But I must say, this is probably some of the earliest work I've seen where sodium-ion intercalation has been reported. So this gives the hope that it is possible.
Yeah. No, I mean, if lithium goes in, there should be a way for sodium to go in. I mean, that's chemistry, of course. Maybe it will be not economical or unfeasible at industrial scale, but there should be a way. I think I even saw some announcement that a Chinese company has announced the first car with sodium batteries. I don't know then, when money or marketing is involved, it's always difficult to understand if the science is there, or if it's which kind of claim it is. But but let's take it as a positive sign.
Yeah, I think as far as I know that CATL has started to commercialize sodium-ion batteries. There are battery packs available. You can buy them actually, sodium-ion batteries. And I think there's a company in Europe, in Palermo, which probably was a few years back the leading company in sodium-ion batteries.
Yeah,
but
I mean, in theory now, I'm really curious to follow this thing because this car company now, I don't remember the name, says that I mean, it's not a battery, it's a car. So in theory, we could buy it and maybe crack it open and check if there is sodium inside. That will be a very interesting experiment because, especially with graphene, we have done in the past that there are products that claim to have a kind of technology inside, and we did it. We open it and we check if there was truly that material inside.
And what was your conclusion in most of the cases?
Well, for as example, the tennis racket,
Yes.
there is truly graphene in it. Also, all this graphene-based heater for your neck. You know, if you go on Amazon now, they claim that graphene emission in the infrared penetrates the skin, the body much better than a metal heater. And also there, it's truly CVD graphene. My colleagues published a paper on also just to describe it. In other cases, like I remember the graphene socks or graphene underpants, I will not buy. It's not that it doesn't work. I mean, you can get your private part black at the end of the day. That's not nice.
Yeah, I think there was a product in the market in Australia which was a graphene incorporated mattress, and apparently, but I think the claim was that it dissipated your heat faster than normal mattress, and then you could sleep better. That was kind of the claim.
Yeah. I think we will need somebody to take these things and really do a test on it. The fact is that then you don't publish on Nature or Science, so nobody does it. But it will be really interesting to see all these claims if they really work.
All righty. Yeah, I agree with you on this counts. Are there any questions from other than myself? Because I don't want to take all the time.
Very good.
All right. I guess I think in that case we might have to thank Vincenzo for his wonderful talk, and I think it's an eye opener in many aspects. Because our team at Monash, we do a lot of work on the energy storage area. You are aware of this. And some of the insights would be very useful for the next generation. Oh, there is a question here. I can see a hand. Dennis, yes.
I think it was clapping hand. It was clapping.
Oh, he was clapping. Okay, he was not asking a question. Okay, fair enough. All right, so I think
I can tell you good night, and well, for you is maybe good day.
Morning. Good day.
Good morning. Yeah, good morning. And Mainak, thanks again, and hope to see you soon, maybe at some conference. If you come to Europe, let me know.
I'm trying to attend the ChemonTubes in France. Are you visiting?
Oh, good. Okay. Yeah, I was also considering. I'm not sure I will be able to go, but I will like ChemonTubes. I really like it a lot.
Fantastic.
I think it's.
Thank you, everyone. Thanks, everyone, for joining the talk, and let's thank Vincenzo once again.
Okay, goodbye.